All right, so I had given you two homework. I remember I gave you a bit less than what's on the syllabus, because but this the only important thing here is finding limits. As you will see, this is something that will come back in the next sections, but all the rest I don't want to spend too much time on. All right, so the first one was number 27, and that was asking what is the limit of the sequence that you have n squared over 2 to the n. And this is for n going to infinity. Okay, so what you normally do is you plug in infinity to see what you get. Infinity over 2 to the infinity, which is also infinity. So we are in again an indeterminate form, so we need to do something. It's a quotient here, so definitely the L'Hopital's rule is something that we want to try. So let's do the L'Hopital's rule. Please go review if you don't remember anymore what it is. I did an example in the video from last lecture. Okay, so first of all, of course, what we need is a function that we can use, a real function, not just a sequence. And so here, that is very easy. We have x squared over 2 to the x. We just replace n by x. And these are well-defined functions. And then by L'Hopital's rule, so the L'Hopital here, do it here, the limit can also be calculated by taking the derivative. So I'm going to take the derivative of this, which is 2x. Take the derivative of this. Now this might be something you don't remember anymore. So let me remind you that the derivative of an exponential function, of course, if it's the e to the x, we know derivative is just e to the x. But if the base is not e, we have one extra coefficient coming in, namely ln of a times a to the x. So we have this extra coefficient. If a is not e. If a is e, by the way, ln of e is 1, so that's why we don't see it, but it's actually there. Okay, so this is ln 2 times 2 to the x. If I plug in infinity, I get still infinity over infinity. But we should check, is this now, did we improve or not? And we did, right? Because this was quadratic here, now we have 2 to the 2x only, which is only linear. So we should try it again. So again, we do L'Hopital. That means that I'm now going to take the derivative of this top function, which is just 2. The derivative here, of course, we have this constant ln 2, and then I have to take the derivative of this, which we already know what it is, that is another ln 2 to the x. Now if we plug in infinity, get 2 over infinity, which is well defined. We know what that is 0, and we are done. As simple as that. Okay, the other question was number 46. And that was asked us to find the limit of, calculate this limit for n going to infinity. The sequence was inverse tangent, but remember I prefer arctangent, of n squared. If I plug in infinity, what we can do here, well, first of all, we should know how the arctangent looks like. Okay, and so the arctangent itself, arctangent n squared, of course you could graph that too and see what happens, but let's talk the basic function arctangent. The arctangent, we have now several times discussed this. So here is the origin. It goes something like this. We have an asymptote, in fact two asymptotes, two horizontal asymptotes, and they are at minus pi over 2 and pi over 2. And this comes from the fact that this is just the rotated version, or the symmetric version, the mirror image of the tangent function, which is of this shape, where the tangent is undefined for these angles, where the denominator cosine gets 0. The difference, of course, is that in the case of a tangent, you get a similar pattern that repeats itself over and over. But when we take the inverse trig function, we always look only at one piece. And that gives us, if we flip this over, we get this piece. All this to say that we see that if you go to positive infinity, so if you go there, you end up at pi over 2. If you go in this direction, you end at minus pi over 2. Now, where are we going? Well, the correct way to say this, of course, but I understand if you do this much quicker, is to say, well, we can bring the limit inside. I talked about this already before, that when we're dealing with our functions, which are always continuous, we can do this. Right? And then we get the arctangent of infinity. And we just argued that the arctangent of infinity, well, it's a little bit, it's actually the limit, of course, for n going to infinity, x to infinity, that is equal to pi over 2. And that's the answer. Okay? All right. So that's all that I want to do for this problem, and then we're going to now lecture on series.